Hey guys, so this video is going to be about precipitation reactions. So remember, precipitation reactions are a type of double replacement reaction. So I'm not really going to cover that in this video. You might be able to see how I'm doing it, but if you need to go back and look at double replacement reactions, that's how you would determine what product is being formed. Okay, so precipitation reactions are chemical reactions in which a precipitate, and a precipitate is just an insoluble salt, so it's a solid, and those get formed through these reactions. So if you remember the video, the previous video to this, where we talked about solubility rules, so any of those salts that would come up as insoluble would be considered a precipitate if it was formed as a product by the reaction. All right, so they can be formed from a solid and an aqueous solution, but most of the time you will see precipitates produced from two aqueous solutions. So aqueous means that it's dissolved in water. So for it to be aqueous, it has to actually be soluble in water, right? So an aqueous solution, they have to be soluble. And then a precipitate or a solid is insoluble according to the solubility rules. So you have to use the solubility rules to determine if the product is actually produced. All right, so here's a simple example, all right, where we have salt, table salt, NaCl, that's been dissolved in water, so it's aqueous, right? It's dissolved in water, and we're also adding to that another solution of silver nitrate, and then our two products here are silver chloride and sodium nitrate. So if you look here, so this solution on this side is going to be the sodium chloride, right? Let's see what I got here. So this is going to be sodium chloride, and then this one over here is silver nitrate. And so you can look, if this little spot of this solution was blown up, you can see the sodium ions dissolved and the chloride ions are dissolved. So that means it's all dissolved in solution because they're separated, right? That's what happens when one of those crystal lattice structures dissolve in solution, they separate. And then over here we have the silver ions in the solution, and then we have the big nitrate ions with the, right, it's NO3. Okay, so NO3 with a -1 charge. All right, and if we put both of those solutions into this beaker, so we add them both together, we get this fantastic drawing, if I do say so myself, of a solution, and we get this white precipitate at the bottom of the flask here. Does everybody, so you can see there's a white solid that has formed at the bottom of the flask. All right, and so if we blow up that circle, and that circle is taking part of the solution, right, part of the solution up at the top here, and then part of the solid down here at the bottom. And if we look at that, this forms that crystal lattice structure because it's insoluble. And so a solid forms as soon as those silver ions and chloride ions meet up. And then the sodium and nitrate ions still stay dissolved in the solution because it's not insoluble, it's actually aqueous, right? So this S down here means solid. It doesn't mean soluble, it means solid, which means insoluble. I know that can be confusing sometimes, but that's just the way it is. And then the AQ means aqueous, all right? Okay, so if we look at that reaction a little bit closer, we have the molecular equation, which is just the complete balanced reaction, what you're used to writing. So we have sodium chloride plus silver nitrate goes to silver chloride and sodium nitrate, right? And then we have the complete ionic equation. So what the complete ionic equation does is it shows what's actually in the solution. All right, so we have the sodium ions, the chloride ions, because this dissociates into those two things when it's in the solution. So it's not really sitting in the solution as sodium chloride together. It's sitting in the solution as sodium ions and chloride ions separate from each other. And the same thing is happening with the silver nitrate, right? It separates into those two ions in the solution. So even when it's sitting by itself in water, it actually looks like this. It's not together like up here. All right, and then when we mix these two into the same container, so we put them both in the same container, the silver ions and the chloride ions, let me grab a different color, the silver ions and the chloride ions are attracted to one another, and once they hit each other, they can't dissolve again. So it forms that solid at the bottom of the beaker that we saw. All right, and then the sodium and nitrate, they're always soluble, so they stay dissolved as those ions. All right, and then we can write reactions, and we typically write reactions as net ionic equations because it only shows the reacting species. So it only shows the ions and the products that are formed. All right. So what we remove is we remove what's called spectator ions. And so in this reaction, the spectator ions are going to be the sodium, the nitrate ions, because they're not changing, they're not doing anything. So I like to think of them as they're just spectating silver and chloride making silver chloride, right? They're just watching these two ions form this compound, all right? They're not actually participating in the reaction, they're just spectators. So we actually remove them because they're not changing chemically. They're chemically the same thing on the reactant side and the product side, all right? So we get this as our actual overall reaction because that's the only thing that's reacting. So the net ionic equation removes those spectator ions out of the complete ionic equation, and then we get what is actually happening. All right, so here's a few examples. All right, and so we want to determine if the reactions produce a precipitate. If so, write a balanced molecular, complete, and net ionic equation and circle the spectator ions. All right, so number one, right, is we're going to have Ki plus lead-2 acetate. And we want to know what products will be formed because we have to write the molecular equation first. So I'm going to look at this, and I've got K plus and I negative. Those are the two ions. And then we have lead-2 and acetate. And acetate has a -1 charge. All right, so if we do inside with inside, outside with outside, we get potassium acetate. And we get lead-2 iodide. All right, so if I look at the solubility rules, acetates are always soluble, so this one is going to be aqueous, and this one is going to be solid because halogens are insoluble with lead, silver, or mercury. Lead, silver, or mercury. So this does form a precipitate, and the precipitate is going to be the lead-2 iodide. And we need to make sure that this is balanced. Right now it's not. So I have 2 iodines on the product side, so I need 2 here. And then I have 2 potassium, so I need 2 here. And then I have 2 of the acetates and 2 acetates, so this would be balanced now. All right, so now I need the complete ionic equation. And the complete ionic equation we're going to separate everything that's aqueous. And so these are both aqueous here. All right, so we've got 2 potassiums plus 2 iodides because I have to keep this constant, right? I've got 2 of both of those, plus 1 lead-2 ion plus 2 acetates. And then we will get 2 potassium ions, and 2 acetates, right? And then I've got 1 lead-2 iodide. And that's a solid. So that would be my complete ionic equation, right? And then my net ionic equation is going to be without the spectator ions. So the spectator ions here are going to be the potassium ions and the acetate ions because they're not changing into anything new. Whereas if we look at the iodine and the lead, they are changing into something new. They're forming this insoluble salt, PbI2, there we go. And so that's the net ionic equation. All right, so that's number 1. And then number 2, okay, we have calcium chloride plus barium hydroxide. Okay, so I need to look at my ions and figure out what I've got going on here. So calcium, chloride, barium, hydroxide. All right, so it's really important that you learn those ions quickly. All right, so outside with outside, inside with inside. Make sure you always put the cations first, the positive ions first. So I've got calcium hydroxide plus barium chloride. All right, and if we look at our solubility rules, this is aqueous, this is aqueous, this is aqueous, and this is aqueous. And these are strong bases as well, the barium hydroxide and calcium hydroxide. So since everything is aqueous, if we go to write a complete ionic equation for this, then we get, and it is balanced already, we end up getting something that looks very strange. Okay? There's absolutely nothing produced here. All we did was mix a solution of this, right? That was in one container with this. And so they're just all mixed together now. Nothing new was formed. No reaction took place here. So we would actually label this NR, which stands for no reaction, because there's no precipitate formed. So this doesn't, nothing's happening. All right, and there's no net ionic equation because there's everything cancels out. They're all spectator ions. All right, and then number 3. All right, we've got aluminum sulfate and calcium bromide. All right, I'm going to have to erase this. And so that's going to give me, if I look at the charges, aluminum is +3, sulfate is -2 charge, calcium +2, bromine is -1. So outside with outside, inside with inside, we get calcium sulfate plus aluminum bromide. All right, and if I look at my solubility rules, this one is solid. Everything else is aqueous. First, I need to balance this equation. All right, so if I'm going to balance this, I'm going to start with aluminum because it's a metal, right? And so I'm going to put 2 here, which changes my bromine to 6 altogether. So I need 3 here. And then I have 3 calciums, so I need 3 calciums. And then I have 3 sulfates, so now it's balanced. All right, if you need help reviewing how to balance equations, all you have to do is ask. It's really not as hard as it looks. So I've got 2 aluminums and 3 sulfates. Whoops. And 3 calciums plus 6 bromides. And that's going to go to 3 calcium sulfates plus 2 aluminums plus 6 bromides. All right, so my spectator ions here are going to be the bromide and the aluminum because they're still in ionic form on both sides. So the only change was the 3 sulfates reacting with the 3 calciums to give me the 3 calcium sulfates. And so I can write my equation, my net ionic equation, sulfate plus calcium goes to calcium sulfate. And I can get rid of the 3's because they would all cancel out. All right, so that's my net ionic equation. This should really have aqueous here. It's not really necessary, but I think they want you to put it on there on the AP test if you have to write an ionic equation. Just know that ions are always aqueous, or gases, but they would have to tell you that. If it doesn't tell you that, you assume that it's aqueous. All right, so there's that answer, and then here's the answer, the main answer for this one. What ions will always be spectator ions? Things like nitrate, the alkali metals, because they're always soluble. So anything that says always soluble on the solubility rules are always going to be spectator ions in every situation.